think October 9th, something like that.
Okay.
Oh.
Okay. There were a couple other announcements as
October
well.
7th.
Can you please
Page. Number means to be confirmed, I think. It says TV, so
Oh, okay.
the location is to be determined, not to be
Yeah.
confirmed in a time, so there is some time.
It's at lunchtime.
Lunchtime.
Okay, well, thank you very much. Maybe we can start, and I'm sure few people will be trickling in. This is one of our informative lunch meetings on a nuclear fuel cycle. So thank you for participating. And this is the lecture 3 out of. We started with the general idea of what's a nuclear fuel cycle, and now we're going a little bit in more details. The previous lecture was on fuel fabrication. Now it's on the power plant. The next one is on waste. So as we were discussing here briefly, the next lecture would be in October 9th? 7th, sorry. And we still need to determine whether it's a lunchtime talk. There are a few other events that I would like to make you aware of if you've seen the circulation around. We have a workshop, 2-day workshop in October as well, 13th and 14th. So there's few spots available for that, and the topic for that is conflict resolution. And with Parina Namaze. And that's after work. It's one day is 3 hours, the other day is 4 hours.
No, two.
3 hours.
1 3 hour, second is
2 hours workshop, and it starts at 4 o'clock or something like that. There's a cost associated with that, so it's a €90 cost for the 2-day workshop. However, if you're a member, it's only €30. So for the ones that I think I see all members here. So thank you very much. I think there were a few other activities that we're planning on. Those will be advertised in due time, and also on our website. So check those. Our website periodically. With that, I would like to introduce Susan Picket. She volunteered her lunch here to talk to us about the nuclear power plants and reprocessing. She's currently with the Safeguards Training Office, and she's one of the training officers, senior, and she was responsible for a couple of projects in the training office, the virtual trainer, and she will talk to you more about it. She has really cool walk through a power plant and other facilities with animation, and she will talk to you about it too. So with that, I would like to welcome you to our Women in Nuclear Fuel Cycle series.
Thank you, and thank you for coming and letting me talk about nuclear power plants and reprocessing. Hopefully I won't put you to sleep. I do have a couple of videos throughout, and we can go to the first slide, John. So you've had the talk on the overview of the fuel cycle already, and I just wanted to highlight the front end and the back end of the fuel cycle, the front end being all of that prior to going into the nuclear power plant, so the mining and milling, the conversion which you had. Have you had a talk on enrichment yet? Or will you have a talk on it?
It was covered in the...
It was covered by Eva slightly.
Okay. And then fuel fabrication, and so now we're here at the power plant today, and so we'll go through the general overview of nuclear power plants. How many people have been to a nuclear power plant before? Oh, okay, super. So then you guys can jump in and talk about it. And then we'll talk about reprocessing. I'm not going to talk about spent fuel management too much. I'll just touch on it a little bit. And I believe high-level waste and radioactive waste management is the topic of your next talk. That said, there's two main types of fuel cycles, which I believe you are familiar with. the closed and the open fuel cycle. Closed being the one that includes reprocessing, open being one that where they take the spent fuel out of the reactor and it goes directly to a geological repository, or interim storage until the time in which they can find a deep geological repository into which to put the fuel. So, okay, next slide. I thought just a reminder of how much nuclear power contributes to the world electricity. It's at about 14%. Net installed capacity is 372,000 megawatts electric. There's 437 nuclear power plants in operation, over 100 of which are in the US, I think about 70 or so in France, and then Japan has about 50, most of which are all shut down at the moment. So that figure actually, I'm not, we should probably check that, make sure it's including or not including the Japanese. I know it is including Japanese, but a lot of those are not really running at the moment. And then the rest, the thing that surprises me on this is coal is at 41% with all of the talk of global warming and whatnot. Still a huge amount comes from coal. This is from National Geographic, which actually has a really neat link and interactive electricity generation site. It's at the back of the presentation, which I'll distribute as well by email. All right, the next slide. So there's lots of different types of reactors. A lot of those are chosen in terms of which country has developed which type of reactors, really based the decision on historical issues or the type of resources there. Pressurized water reactors, boiling water reactors, and I'll talk more about how they operate, but I just wanted to give you a snapshot. RBMK, and also in the pressurized heavy water reactors are the VVERs, which are the Russian pressurized water reactors. This is by far the largest number of reactors are this type, and then boiling water reactors and pressurized heavy water reactors, which are, these are interesting because they are on-load reactors. That means they don't have to be shut down to be refueled. So you can push the fuel through while the reactor is operating, which has interesting implications for safeguards, but that's not the subject of today's talk. And then in terms of percentages of them, again, this is basically the most of pressurized water reactors down to the fast breeder reactors, and we'll talk a little bit of that as well as we go on. And I'll get into the enrichment, moderator, and coolant and what those are. So, next slide. I thought this was interesting just to give you, again, a snapshot of where we are in the development of nuclear power. It started back in the 50s after World War II. The United States developed their reactors really based on look at submarines and what they were designing for the submarines at the time. And the U.S. went forward with light water reactors, pressurized water reactors in particular. Canada went ahead with pressurized heavy water reactors, in part because they have huge amounts of natural uranium resources, and the PHWRs do not require the enrichment step that's required for the pressurized water reactors. So, and as we've gone forward to generation 2, this is most of the reactors operating today are what they consider generation 2 reactors, and they've been in operation for many of them, definitely over 30 years, going on to over 40 years. A number of them have been relicensed to operate for much longer times. And then we move into generation 3, and this is kind of what's being built now, is the generation 3 reactors, and those are the newer reactors. And they have things like what they call passive safety, so that if there's an earthquake, it's more like they're more ready that the control rods will go down and shut down the reactor, and so that there's less mechanical things that have to be done in order to ensure the safety of the reactor. Some of the things that they're looking at in terms of generation 4, and it's funny, it's a little slower moving ahead than I think originally intended, but they try to look at highly economical, of course, enhanced safety, minimal waste, proliferation resistant, and that's an interesting challenge to try and make a reactor proliferation resistant, because it's really, you need the fissile material to make that reactor go. some of the challenges as nuclear power continues to develop, and I'm sure you're aware of these. So what are the challenges? Why might nuclear power not move ahead as fast as we think it could? Expensive at times, depending on your cost analysis.
Safety.
Safety, yeah, Chernobyl. I mean, after Fukushima, there was a huge, Germany said, no, we're going to shut down the stop our reactors from being huge. Safety is a huge issue. Public confidence, I mean, that kind of all contributes to public confidence in what the government is deciding. Japan is facing that a huge right now significantly, and yet where does a country like Japan get the rest of its nuclear, rest of its electricity? And so then you look to shift to oil or coal or natural gas, and then you have the global warming balance. Non-proliferation also is an issue, but I don't think, in terms of nuclear power going forward, I don't think non-proliferation is kind of the showstopper there. I think a lot of it is definitely much more the safety of the general public confidence in nuclear power going forward.
Do you think that there's no technical challenge to solve those problems? This is more kind of the external factors?
It's interesting.
Because if it was so simple, why wasn't it solved yet?
Yeah, I don't think it's so simple. I don't think it's more of a socio-technical problem. I'll quote a former professor of mine that it's the whole system of nuclear power in a lot of ways, and managing it. I mean, since the start of atomic energy and atomic weapons and nuclear power, how do you manage this as a social system? And it's the same issue that we're saying with deep geological repositories and finding a place for the waste. Many scientists will say, yeah, technically it's fine. We'll put it in some salt, put it in the ground, and it's geologically stable. But when you come to, you have multiple perspectives in the public and resolving that. I was reading an interesting paper by the former head of the Japan Atomic Energy Agency that went into a lot of those issues in trying to look at Fukushima and where does Japan go ahead. And his premise is that, no, it's not just an easy technical solution, that we actually have to look to manage it safely, and how do you get the human organization around nuclear power in line so that nuclear power can be a technology, but that one that is management. So I think it's a very big challenge.
Susan?
Yeah.
Is one of the issues also that the advanced generations are much more complex, we use liquid metal and things like that, and so the safety balance and increased complexity is greater issues.
Well, I think, so you have the kind of the two sides. So if you have the advanced ones being the fast breeder reactors where you'll have the liquid metal, I think those are slower to develop for a lot of those reasons. But I think the advanced light water reactors are kind of moving ahead, and at least from what the designers have said is that they do include, they're trying to make them simpler systems with more passive safety type of things in them, and simpler to manage in that way. So basic operation of a nuclear power plant. I thought we'd just go through this quickly, and then go through the main features of it. So in the reactor, you have the reactor core, and that's where the fuel is. So inside the fuel, and I forgot to bring my fuel show and tell, because it's really heavy to bring all the way down here. But if anybody's interested, I always welcome show and tell. Please give me a call, an email, and I can show you sample fuel assemblies and our safeguards lab. I'm happy to do that anytime. So in the reactor, you have the fuel, and inside the fuel, you have the fission reactions that go on, creating heat, basically. And that heat is used to heat up the water and create steam. That steam is then used to drive the turbine, which turns the generator to create electricity. It's just like all the other power plants, except the fuel differs, and this one the fuel differs. The other thing that's also important in reactors is the control rods help control that reaction, and the containment structure is put there for safety. It's defense in depth principle, so that if something were to happen, it's contained within that huge thick wall concrete structure. If you go ahead and click on this, there's a video.
Which one? Oh, okay, back.
Yeah, oh, yeah, go back. And just click, click anywhere. Yeah, and show the video. I'm just gonna talk through this video, because the volume on this one doesn't work. And I've tried it numerous ways, but I really like the video. So this gives you an overview of the facility itself. So it's not just the reactor, and the fuel actually takes up probably as big as this room, and that's about it. So inside the pressure...
Can you maximize the video?
Can I maximize the
Yeah.
please?
Inside is the core, and so that's where your fuel will be. And then I like this visualization. So you have your neutron that's hitting your uranium-235 atom, causing it to split into fission products. So those are the fission products, and we'll talk more about those later. But then you have a chain reaction. For each fission, there's about 2+ neutrons created that go on to set off another fission. The fuel rods simply produce heat. That heat is then used to heat up the water. The control rods here absorb the neutrons and moderate the reaction rate. So the control rods are made of things that can absorb the neutrons so that you don't have too many neutrons setting off too many fissions, because you don't want an uncontrolled chain reaction, which is what happens in a nuclear weapon. And then that is used to create steam to drive the turbines. Condenses water, the water then goes back in, so you condense that water, goes back in to be reheated and start the process all over again. And in a pressurized water reactor, you have a primary and a secondary loop. In a boiling water reactor, the water boils right in the core, and then that is what's used to drive the turbines. So you don't need a steam generator like you do. The concept with the boiling water reactor was that they thought it would be easier and simpler, to Jane's point, and yet there's other complications with that reactor design. One of the things that I think is interesting, in the boiling water reactor, the control rods come up from the bottom, whereas in pressurized water reactor, they come down from the top, which, as you think about gravity, it's nicer that they come down from the top, in case your diesel generators don't work. So that's the basic operation of a reactor. Okay, next slide. So reactor classification. So this is generally how reactors are classified. As I said before, there's about 6 main types. Nuclear fuel, it'll be uranium, plutonium. Thorium is kind of a development of a fuel. In India is primarily looking at using thorium as a fuel because it's got huge amounts of thorium resources, but it's not necessarily, not in operation yet. Fuels have different enrichment. So natural uranium is 0.7% of U-235. In order for it to be made into fuel for light water reactors, so your pressurized water reactors and your boiling water reactors, your VPDs, you want to enrich that for 2 to 5% of the isotope U-235. So most of your fuel is U-238, but 3 to 5% will be U-235. In pressurized heavy water reactors, your on-load reactors used in Canada, in India, Argentina, Romania, it will be natural uranium is your fuel. And I'll show you some pictures of the fuel. Fissile material production. So most of the reactors in use today burn their fuel. It's irradiated and it reduces the amount of fissile material. If it produces more fissile material, it's called a breeder reactor. Moderator. The moderator, again, is the material used to slow down the fissions to thermal energy. So basically, you're slowing the neutrons, so it has a better chance of fissioning that U-235 atom. That's the key. So if you think of, if you're playing, I don't know, if you're trying to hit a baseball or something, it's much easier to hit it if it's going slower than if it's going fast. Neutron energy distribution, and again, this deals with how fast those neutrons are. If they're faster, thermal neutrons, thermal being slow. Coolant, that's the material used to extract the heat from the fuel, and that's usually in light water reactors, it's light water, or it could also be gas or air. And then the power cycle arrangement is just really the arrangement for transferring the heat from the reactor to the steam turbines. So on the fuel, I thought this was good to give you a sense of what that fuel is. The can-do bundles are about this big, and that's in the pressurized heavy water reactor. And they're about this big, and they weigh about 50 kilograms, to give you a snapshot. We have a real good mock-up upstairs. And then these are just pictures of, and these are tall, these are about 3 meters, of each of the different types of fuel. This is the Magnox fuel, which is a metal fuel, which is used primarily in the UK, and that's your fast reactor fuel. This is also the advanced gas-cooled reactor fuel used in the UK. And you all had the fuel fabrication lecture already. The other thing, I can send out, if you want, I have this electronically, and I'm happy to send it. Interesting. All right, so next slide. I put this down just to show you the process again, but since you've already had the fuel fabrication, I'm not going to go through it too much. The one thing I do want to mention is the mixed oxide. So when we start talking a little bit about reprocessing, the purpose of reprocessing is to take out from that spent fuel the usable material so that you can reuse it to fabricate new fuel. That fuel is referred to as MOX, or mixed oxide. It's a combination of plutonium and uranium oxides. And this is pretty much your process. And I think fuel fabrication is great for like a discovery of how it works, because it really is an industrial process that you're talking. It's like making pills or candies or anything. It's really a process of taking the powder, compacting it, sintering it, making sure it's warm enough for baking it, and then you compile it and you stack up all these little pellets into a big rod, boom, put it in a fuel assembly, put it in the reactor. People that are really experts in fuel fab would probably laugh at my short and sweet example. The interesting thing about MOX is because it has plutonium in it, this fuel fabrication is done inside glove boxes. So it's inside, you have to be separated for your own health and safety issues. Okay, and so then, all right, so a review of this. Again, the fuel material, so you have your different types of reactors. You have light, low enriched fuel, or MOX, can be used in your PWRs, BWRs, pressurized heavy water reactors is natural uranium. And then HTGRs and GCRs, so high temperature gas reactors or gas cooled reactors. The high temperature ones are the newer reactors, some of the newer reactors, and they'll use a combination of almost anything. Gas cooled reactors use natural uranium. Again, the gas cooled ones are used in the UK. It's also the Magnox reactor, is also what North Korea has developed as well. And then your fast breeder reactors, they'll use plutonium or with a mixture of natural uranium or DU, depleted uranium, or they'll use MOX. Fissile material production, as I mentioned before, this refers to how much material you have at the end after the fuel has been in the reactor. And on that, so the fuel will stay in the reactor for a light water reactor, anywhere from 3 to 6 years, depending on the burnup and what that reactor is operating at. And they won't refuel. When they refuel the core, they'll take out only parts of the core at a time. They won't take out all of the fuel at the same time. The moderator material, again, this is what moderates those reactors. So your general moderator materials are water, heavy water, graphite, and then the coolant, the neutron energy, again, we referred to that before, and then the different types of coolants that you'll have in that, and that's what's used for your heat transfer. So that's just visually working. All right, so let's go on a tour, and this is a pressurized heavy water reactor.
This is a pressurized heavy water moderated and cooled on-load reactor using natural uranium oxide fuel. These reactors use natural uranium fuel and use quasi-continuous refueling. Most reactors have a once-through fuel cycle with long-term wet and dry storage of the spent fuel on site. There are over 30 of these reactors, both single and multi-unit stations, in operations around the world. This tour will guide you through a single-unit station. It is important to remember that there are variations in design between single and multi-unit stations. New fuel arrives in pallets of 36 fuel bundles, weighing 1,000 kilograms, and is received in the new fuel storage room in the service building. Each fuel bundle contains approximately 19 kilograms of uranium. This room accommodates 6 months of fuel inventory and can temporarily store all fuel required for the initial fuel loading. The fuel bundles are transferred to the new fuel loading area in the reactor building through the main equipment airlock. Before being irradiated, natural uranium fuel can be safely handled manually. In the new fuel loading area, the pallets are unpacked and 8 bundles are loaded manually into the magazines of the new fuel transfer mechanism. This may differ at multi-unit stations. The fueling machine clamps onto the new fuel port and fuel bundles are transferred into the fueling machine. The fueling machine moves to the reactor face of the calandria. After removal of closure plugs and shield plugs from both ends of the channel, new fuel bundles are pushed into one end of the channel and an equal number of spent fuel bundles are received by the opposite fueling
So
machine.
this is the fueling
To support
machine.
the loading and unloading, the push is usually performed with the flow direction of the cooling water.
And each
Each
bundle
channel
is pushed into the
12
channels, and
bundles.
those are the channels.
The typical core inventory of a 600 megawatt reactor is 4,560 bundles. To achieve a more uniform burn-up distribution, only 8 of the 12 bundles of any given channel are placed. Normally, 2 to 3 channels are refueled daily. This refueling schedule differs depending on the reactor and the operation schedule. At some multi-stations, fuel channels hold 13 fuel bundles with a total core loading of 6,240 bundles. The fueling machine containing the spent fuel moves off the reactor face and travels into the fueling machine maintenance lock, where it locks onto the spent fuel port and discharges the bundles. Irradiated fuel bundles are pushed 2 at a time into the ladle of an elevator, which lowers them into a water-filled discharge bay. The elevator is lowered underwater and the fuel bundles are deposited on a transfer conveyor. Irradiated fuel is taken out of the reactor building via conveyor belts through the transfer canal into the reception bay. Here, the fuel bundles are transferred to a spent fuel storage tray. This operation can be done manually or in some cases automated. Trays of spent fuel can be lifted using a lifting tool, and the gantry then transferred to the main storage bay through a conveyor. Similarly, defective fuel is transferred to the defective fuel bay and may be placed in cans. When suspected defective fuel is discharged, the fuel bundle is first placed in the defective fuel carousel for some days, and then later moved to the reception bay and into the defective fuel storage bay. Operations in the storage bay are carried out underwater using special tools, aided by cranes and hoists. The main storage bay has sufficient capacity to store up to 10 years accumulation of irradiated fuel. After the irradiated fuel has had time to cool down, usually 6 years, it can be moved to a permanent dry storage location. To prepare the fuel for dry storage, full trays are moved to the back of the storage bay. The trays are positioned in a tilting mechanism which lifts the bundles and places them into a spent fuel basket, which can hold up to 60 bundles. The basket is moved underwater and lifted into a shielding and welding station. The loaded basket is then dried and the lid is welded. The basket is loaded into a shipping cask through the bottom. Finally, the cask is moved to the shipping room and placed on a flatbed truck for transfer to dry storage. Different reactors may use other type canisters and modules into which to load the spent fuel.
Question about keeping spent fuel for cooling.
Yeah.
It still generates energy, right? Because
Yeah, it's
so is this being somehow taken advantage?
it should be. I mean, you would
Not
think.
really. No.
No, you would think it could be. I mean, I think that's the huge problem with energy today. We don't take advantage of.
We're wasting so much.
Yeah,
I mean,
we
I was
waste
the
a lot.
energy efficiency of most of the generators are, I think like
It's
20 or 40%.
30%.
I forgot the science, but it's well, it's like.
Yeah, it's around 30%. So I mean, the heat generated in a nuclear power plant, so your megawatts thermal is much higher than, it's about 2-3 times higher than your megawatts electric. So yeah, the conversion rate is not nearly. We have lots of room for improvement, lots of room for evolution. Spent fuel management, yeah, as she says, yeah, maybe we could tap into that a little bit more. So after irradiated in the core, it's then removed, and in that last video we showed a pressurized heavy water reactor, and that stays in the pond for much longer than the light water reactor fuel. Right now the PHWR fuel is not reprocessed, but the main fuel that's reprocessed is from your BWRs and your PWRs or your VVERs. And this will stay in the pond for at least a minimum of 12 months, And then, if it is going to be reprocessed, so if it's not going to be reprocessed, depending on the country, and this is really country specific, as to whether they have a once-through fuel cycle or a closed fuel cycle. The countries with a closed fuel cycle right now is primarily Japan. France does a lot of reprocessing, the UK does some, Russia, China does some. But for the most part, many countries do a direct once-through fuel cycle, so then the spent fuel is left in the ponds, and once it's cooled enough, it's either moved to dry storage or to an interim wet storage facility until a deep geological repository can be found. So I'm just going to focus today on reprocessing, and so they'll take the fuel after it's been cooled, and then they'll move it from the reactor to the reprocessing facility. And it's moved in a canister like this. So as you can see, the canister is, so it'll hold about 24 fuel assemblies, but as you can see, it's well shielded because it's still very radioactive. And the makeup of that spent fuel after it's been irradiated is primarily uranium. You still have a lot of uranium-238, but you also have about 2%, 2 to 3% of that uranium-238 has been converted to plutonium. So the purpose of reprocessing is to try to take out as much as that uranium and as much as that plutonium so that you can then reprocess it, reuse it, and then reprocess it, put it in a form that you can then refabricate new fuel, take that fuel and put it as mixed oxide fuel into your reactor. So ideally it's nice, it's closed. The fuel cycle is very nice. There's been a lot of issues with reprocessing, both on cost, on the economic side. Reprocessing has been extremely expensive. My experiences is with the Japanese program, which Rokashomura has cost over $21 billion, and it's still not running yet. It was initially supposed to run in the 1990s, and it keeps going and going and going. And it was initially the closed fuel cycle. We can optimize resources, we can use all of the uranium, use all of the plutonium. Reprocessing's turned into a lot of ways a spent fuel management tool, in Japan at least, in terms of what do we do with all of this spent fuel. We can't keep it in the ponds. In Japan, it's very hard to find a deep geological repository given the lack of stability of the country in terms of earthquakes. So, that said, so now we'll talk back on reprocessing. So, how do we pull out the uranium and plutonium? So I'll talk a little bit about that. So, next slide. So, separation of the products, as I mentioned, namely uranium and plutonium, to then be reprocessed into a form for new fuel. This gives you a picture of what your uranium fuel going into the reactor is, and then your spent fuel coming out. So it says 97% reusable material. A lot of that depends on who's doing the overall assessment of reprocessing. And so we'll talk about once it's reprocessed, in the process of reprocessing, they pull out the fission products. So the fission products are considered high-level waste. And those fission products have to be disposed of. I'm not going to talk about that again here probably during the waste, but that high-level radioactive waste is usually vitrified, put in some kind of matrix, and then canisters, and then in a disposal solution, usually a deep geological repository of some set. So even if you have reprocessing, you will still have high-level waste that has to be disposed of, and you will still have to find some type of solution, be it a deep geological repository or an interim repository for the next 300 years. And again, that all goes to the state policy, the public involvement process, the overall policies regarding health and safety of that country. So, all right, next slide. The types of reprocessing, and I'm not going to talk about all of them, but I will just touch on them. So there's an aqueous method and a non-aqueous method. The commercial types available today fall into the aqueous method. So we'll go through, and I put this up just so you have a snapshot of it. The two different types, and basically one is to convert to plutonium oxide or uranium oxide. I should also say uranium oxide. But then you could use that to go to plutonium metal for weapons, and the same with the non-aqueous methods. You could convert it to oxide for fuel, or you could look to convert it to plutonium metal for weapons use. Okay, next slide. The history of early development. So of all of the different types, they tried different chemicals starting in 1945. The main focus was on weapons production. Reprocessing didn't really care as much about the uranium, really focused on getting that plutonium out of the irradiated fuel to use for atomic weapons. And they used a bismuth phosphate precipitation process. I'm not going into any of that. Just to give you a snapshot of it. But then there was, Russia used a different process, and it was again focused on military purposes. And then in the US, they tried other processes, but they found problems depending on which chemicals they used in these processes in terms of how do you deal with waste or stability and exposure to radiation. So you have to separate the plutonium out of that fuel, but you have to dissolve it in something, you have to use other chemicals. And depending on the stability or vulnerability of those chemicals to the radiation from the plutonium or the uranium really changed which process could be used long term. So the process we use today that is commercially used today is called the PureX process. So I'll talk some about that. All right. I love this slide because I think it's nice and simple, and it's, to me it gives a great picture. So we talked about once it's been in the pool and it's sufficiently cooled, they'll then take that spent fuel out of the pool, put it in casks, and then ship it to the reprocessing facility. So that's here, it's in the cask. They'll take the spent fuel out of the cask, and then really, quite simply, they'll chop it and dissolve it. So basically, depending on what the clad material over the fuel is, they'll either shear that off or they'll go directly into chopping. They'll then take all that chopped spent fuel, put it in probably a nitrate solution, nitric acid, dissolve it. And then what they try to do is you have to separate the uranium and the plutonium, so they'll separate that out. And I'll show you some videos on that. And that's done with mixer settlers or pulse columns. Any chemists in the room? I'm not either. And so when I see all of this, and they use certain chemicals to try to separate all of the uranium and plutonium. And then they want to purify it. So you have your uranium purification and plutonium purification. And this slide is from Japan. And so then they mix the uranium and plutonium back together. And that, in Japan, that's done for non-proliferation purposes. They don't want the plutonium kept separate from the uranium. And that's very much a national decision for non-proliferation purposes. So they mix it back up together. They also have the uranium oxide at the top, and then the mixed oxide here. And they can use that uranium oxide they might use that back in fuel fabrication, they might send it for re-enrichment, and then this mixed oxide powder will then go to a MOX fuel fabrication, and then it'll go through that fuel fabrication process. All right. So I wanted to give you a snapshot of some of the equipment that's used. And so this top picture is of the chute into the dissolver. So after the spent fuel is chopped, it'll go down a chute like this. And this is in Thorpe in the UK, with inside a huge hot cell, so protected so that it's not exposed, so to protect humans from the radiation. This shows also in the UK sharing of the material around the bar. This is from a gas-cooled reactor, so the Magnox fuel. And Donna, if you click on that, we'll have a video. Oops.
This one?
Yeah.
At the charge bulge, a charge ram pushes the fuel into one of two envelopes fixed to a turntable in the shear cave. The turntable rotates in order to align the envelope holding the fuel with the shearing equipment. A second ram then pushes the fuel forwards into a gag, and the shear blades chop the fuel bundle into short lengths as it's advanced by the hydraulic ram. The chopped pieces of fuel fall through a chute into a perforated basket immersed in hot nitric acid inside one of 3 dissolvers. The chute from the shear cave can be rotated to each of the 3 dissolvers in turn in order to maximize throughput.
And then, once it goes from there, then it goes to the mixer settlers. So this gives you a snapshot of the mixer settlers, and go ahead and click on that one.
Mixer settlers are used in criticality-safe processes, such as uranium extraction and backwash, and for solvent washing duties. Mixer settlers are tanks divided into 2 compartments by special baffles. The solvent and the aqueous streams are fed through inlet ports into the mixing compartment, where an impeller agitates the liquor to ensure maximum contact area between the 2 phases, allowing efficient mass transfer to take place. The resulting emulsion, tiny droplets of aqueous suspended in solvent, flows into the settling compartment, forming a mixed phase. Because the aqueous droplets are more dense than the solvent, the mixed phase separates out into the aqueous and solvent phases.
And then from that phase, and I don't have a, it'll go to precipitation, so then you want to pull out that uranium and plutonium, precipitate out, so then it can be converted into powder. So then the next slide. And so this is the finishing process. So if you click on this, it'll show that too.
In the finishing cycle, steam stripping followed by evaporation removes excess solvent and increases the concentration of the uranium. The concentrated liquor is then fed to 4 fluidized bed reactors, which use the thermal denitration process to convert the uranyl nitrate to uranium trioxide powder. This powder is drummed off into stainless steel drums and moved to the uranium product store.
So a similar process is done for the plutonium as well. Plutonium uses a slightly different process, but basically the same thing. And then that powder will be in Japan, in the case of Japan, mixed with the uranium powder. In the UK, I think it's done separately, and I think it's actually done separately and then mixed at the end at some point to make the MOX powder. And the next slide. So that's pretty much it, overview of reprocessing. And then I just put this up to give you a picture of the types of fuel that are reprocessing and where they're being reprocessed in the world. And that's it. Are there questions, comments? And I'll make all of this available to you. I can give you the whole folder so that you can have the videos as well.
I'm just saying, body water reactor is the one where there's currently water in the car. In the body water reactor, the water is heated directly, right?
Directly,
And then
yeah.
it gets sent to the turbines.
Yeah.
So then
There's no
the turbines are obviously contaminated with radiation.
Yeah.
So how is the maintenance?
I think, and I don't know, I'm not as familiar with boiling water, but I think the maintenance on the PWRs is harder than the maintenance on the PWRs. But the original concept was that this whole thing would be
Simpler. Simplicity.
Yeah.
Yeah, you have one loop of
Yeah.
after the turbines, the water is condensed and it's fed back into the system. But yeah, you're right. Then you contaminate the
Yeah.
turbines. the radiation, as you see, I mean, it's very well controlled outside the containment area.
Well, obviously,
So
the turbines are in temporary.
And the amount of monitoring they do is really, I think, gotten a lot better than it was, at least in the 50s and 60s. I know the US learned a lot from lots of mistakes.
Right, I think in that, I don't know if who of you have seen the Pandora's Promise, the movie that was kind of explained the nuclear
Yeah.
by Oliver Stone, right? It's right now, I think we sent it out, it's Robert. Yeah, he explained actually what's behind it. There were a lot of political reasons why certain reactors were developed and forward, especially, I think even from the beginning that the idea of reprocessing was there, but I think the cost is pushing, took that out of the loop, even from the beginning, even from the 50s, for the nuclear reactors. When it comes to this, but I think the reprocess was always the idea that so we don't have problems with storing the fuel for a very long time, especially if we don't separate the plutonium out of it.
Yeah.
The plutonium life cycle is such a long.
Yeah, and I think it's really, somebody mentioned to me a few years ago, they said, with all the money Japan is spending on reprocessing, they could buy up all the uranium reserves
In the world.
in the world. So why are we putting all this money into reprocessing for this ideal, the sales pitch, but, the rationale being that, well, we have to reuse resources. Well, it sounds nice, but if you look at the economics.
Yeah, actually, I think the problem now is there are a lot of mines, maybe that came to the last, are closing because the uranium is very cheap. The mine and the fuel fabrication. Just per, I don't know, per ton or it's a relatively cheap, and so a lot of the mines are going out of business because they cannot make money. So reprocessing in the long run, once we close all the mines to restart the mine, maybe reprocessing might make sense. I don't know. We'll see if we come to that point. But from the the cleanest source of energy at the point.
There's so much more starting there radioactive waste, so it's expensive, but it generates less waste. So,
and the waste is really not a problem. It's that there's not that much waste generated. I think people think that there's a huge amount of waste, the fields and fields.
Well, and you look at all we use, and I think that's really interesting. You look at all the garbage we generate on a daily basis and what waste is, and I mean, nuclear waste, at a nuclear waste site, it actually looks really nice and neat, and yeah, it's hot and it's dangerous, but it's not what I think a lot of people visualize as waste when we say waste.
Something else that's not very well known is there's a fair amount of uranium enriched in coal. And so when you burn all that coal, you end up with a waste stream that's 5% of the starting coal that has quite a bit of uranium.
Actually,
something like that in it.
And even the radioactive
coal's
products,
radioactive.
right? Yeah,
Coal's
coal,
radioactive.
the release through the stacks and the radiation issues surrounding that. Yeah, and it's not. And so there's other
Publicity. How like coal versus nuclear power. The statistics are huge.
I think a lot of the environmentalists in the 60s had a big influence on how the nuclear power was portrayed at the time, and a lot of them were actually under the influence of the other industries, oil and coal at the time. And if you even think about this, other alternative energies like the solar and stuff, from the waste point of the chemicals that are used in the solar panels are probably even very dangerous compared to some other.
Yeah, and nothing's perfect,
Yes, there's always pros and cons. So.
Both on the waste side, how much you're going to use it, and yeah, nuclear is great for baseload, solar's might be great for intermittent and in certain applications, but you're going to have wastes and pluses and minuses and everything. And it frustrates me because you always get one perspective here, one perspective there, and you really want just a balanced view, but whoever presenting always has where you sit is where you stand, and it's hard to sort out the truth in everything, but say thank you very much.
Yeah.
And again, please feel free to contact me if you want to see mock fuel assemblies, if you want to see safeguard stuff, I'm in safeguards training. I'm
There was a while ago a visit to the safeguards lab. Yeah, we can, if there's interest, we can probably organize some of the labs and or the training center. They have a lot of equipment there. Is that something that you guys would be interested in? Okay.
Yeah.
Definitely, yeah, we can plan. Here's some of the members, maybe, maybe we can discuss that this afternoon for our future activities, to see hands-on things. Well, thank you Susan, very much.